Right, hi everyone. I want to show you how to use OpenVSP to identify an aircraft's neutral point and calculate the static margin for a given center of gravity location. So here let us open our geometry, the good old twin turboprop geometry, which I used in some of the examples. And here is the geometry. My origin for my aircraft model is the center line of the wing leading edge, and that will become relevant shortly. We'll see how that works out. So under analysis, I open VSP Aero, and under overview, we'll do this with vortex lattice method calculation. I find that's generally more robust than the panel method, and it's what I generally recommend for doing these things. I generally like to put in the reference area, span, and reference chord by hand from my own, what I know about the aircraft, or I can compute separately for the mean aerodynamic chord at 1.49 meters. The moment reference position, this is where all the forces and moments are calculated with respect to, and basically it amounts to the center of gravity location of the aircraft. You'll see that I have preset this here to be 0.855 meters behind the wing leading edge. So one thing that is interesting here is to note that OpenVSP, when it does, or VSP Aero, when it does these calculations, it generates what is called a degenerate geometry. For anything that is not a lifting surface, it generates this kind of cruciform approximation to it, and it's going to place panels on each on the subdivision of these kind of cruciform geometries. You'll see it does this for both the fuselage and for the engine nest seals in this case, and they are relevant to what kind of moments would be produced. Under advanced, see the number of iterations for the wake. I think the default value is 5. That allows the wake to move around behind the aircraft to settle down into some kind of equilibrium position instead of trailing straight downstream. That has a minor effect on the outcome, but not all that much. The important thing here is the run mode. Stability type is going to be steady for this analysis. You can leave all the other things be the default values as they come up. And now we're going to launch the solver to start the analysis. You'll see the results manager for VSP Aero get put up here, and you'll see the solver information. GMRes is the generalized minimum residual iterative solver used to solve the vortex lattice problem, and it's solving it as it varies the aircraft's orientation in space. It changes pitch, changes roll, changes yaw, and it changes speed and Mach number, and then it calculates all the stability derivatives that it wants using finite differencing. I think it, for pitch, yaw, and roll, it basically changes the heading by something like a degree away from the direction that you've drawn it. And you'll see there's, according to some of these things, there's some asymmetry showing up in these computations of wing and tail loading distribution. There's a number to run through because you'll see that it's varying the angle of attack and the side slip angle here, and also the Mach number in these iterations. Shortly it'll finish doing these runs. Takes a couple of minutes. Alright, so now it has finished because the iterations have stopped. One thing I should say is here, each of these wake iterations, you're looking for something like a fairly smallish number of GMRes iterations. Here it's taking 4 GMRes iterations to converge through the residuals. That's showing you your geometry is reasonable. If this thing is taking 20 or hundreds of iterations to try to converge each of these things, it might never converge. That's telling you there's something wrong with your geometry, and you might want to try playing around with that before you come to this stage of doing your stability derivatives. Okay, so at the end of the analysis, one thing you'll find in the directory which you ran this in, which originally had your geometry in it, is a file called twin turbo prop rev2, that's the original VSP3 file I had, degen geometry, that's this degenerate geometry, .stab. And in the header of this, you'll see some of the things which were set up in the VSP Aero solver tab spat back at you. And further down, you'll actually see the derivatives with respect to forces and moments. Here it says, with respect to pitch angle, with respect to side slip angle, pitch, roll and yaw, and Mach number and speed. And the thing that we're interested in here is down the bottom. XNP, that's the neutral point position. And here it is telling us that that is just about exactly 1 meter behind the leading edge of the wing. 1.00020219 L units. And our L unit happens to be a meter here, but that's just for the geometry. And it is telling us that for the center of gravity location we had chosen of 0.855, our static margin is around 10%. In fact, it's 9.867424%. So I was aiming, in fact, I'd already done this analysis and I actually set this reference location of the center of gravity to actually give me the required static margin. I was aiming at 10%, and this was good enough. So that is how you get the neutral point location, and then you would go about choosing the center of gravity location to give you a desired static margin. And that is all there is to this analysis. So that I hope that explains it reasonably well.